We're going to talk today about gravitational red and blue shifting of light. Basically, as we talked about in a previous video, we found that gravity affects light because an accelerating frame can make a beam of light appear to bend towards the floor because when it first enters the window, the speed of the rocket ship is slower than as it gets further down, the speed of the rocket keeps increasing. And so from the rocket ship's perspective, it's not that it's speeding up higher, it's that it's in a gravity well, and then the light is bending and speeding up faster and faster downward. So remember, the equivalence principle says we can replace any small scale gravitational field with an equivalent accelerated field. And so looking at this from the perspective of a spaceship accelerating, then the spaceship's accelerating and the beam of light's still going straight. But looking at it from the perspective of the person on the spaceship who says, I'm not accelerating, I'm just standing in gravity, and the beam of light is coming in and curving towards the floor. Basically, was the big clue for Einstein that gravity bends light. And so, other than just bending it with the gravitational lensing and the stuff I talked about before, we can actually have it affect light by giving or taking away energy from it. So what I had here was a person standing on a planet with acceleration g, and then a height delta h up above the ground. We had a little laser beam that was firing out a frequency, a photon of light, and it was going to go down and be caught as a detector. And we wanted to try and figure out what is the difference in frequency of the light emitted versus the light as it reaches the surface and is observed. Okay, and so as Einstein said, if you want to understand gravity, you need to understand acceleration. We can replace this situation with an equivalent accelerated frame of reference, and then whatever happens here is also going to be what happens here because these two are equivalent. So we'll go to this guy in a spaceship. We'll say a laser is still delta H above his head, but now instead of being in this gravitational field, he's in this spaceship that's accelerating at a rate of g equal to whatever this planet was. And so now here, this is an F sub h here. That's a high FH, and that's what it was over here, FH, FL. So FH up here, FH is equal to whatever it is, and then comes down here and it equals FL. Well, you can imagine when this is first fired, it's going to have some sort of frequency, but as it goes towards the bottom of the spaceship accelerates faster and faster. So by the time the spaceship reaches the beam of light, it's going faster than it was when the beam of light was emitted, and that's going to cause this beam of light to appear to be compressed, which is going to be a higher frequency than what it was emitted at. So this would be a blue shift. It shifts from low energy to high shift. So blue shift is the higher energy side of the visible light spectrum, so that's what that blue shift means. And so that means that same thing would happen here. A low frequency wave shot up here would be higher frequency by the time it reaches the ground. And then of course, you can do the exact opposite of this. If you fire something up, then its energy here, if you want to think of it this way, the energy and the frequency it has here is going to go and become more redshifted. It's going to be a longer wavelength. The red is the longer wavelength in the visible light spectrum. It's going to shift over towards the red side, to the longer side of wavelengths as it travels up. So if this guy was holding the laser and shooting the laser light up, by the time it got detected up here, it would be a lower energy photon, a higher, a lower energy photon, a longer wavelength, a lower frequency. So there's a couple ways you can actually go through and calculate this. One is, I believe, by just doing the old Doppler shift kind of thing, and you could sit here and work this all out and get it right. Another way is just to, in a simpler way, is through conservation of energy. So here what we're going to say is our energy initial is equal to our energy final. Okay, in this case, this is final and this is initial. And so energy initial, that's going to be the energy of the photon up high plus its gravitational potential energy. So E sub g, and that's got to just equal the energy of the photon down low, E sub L, at the low end. So here it has potential energy on this side, over here it doesn't, it's reached down to the ground. The energy in a photon of light is equal to E equals hf, and this will be the up high frequency, plus, and this is going to be a little weird, but we're going to put mgh here for the photon, even though the photon doesn't have an inertial mass like that. We're going to go ahead and put it there, and then over here, of course, hf low, and that gives us this. Now, so what are we going to do with this mass? We're going to have to take care of that in some way, and thankfully Einstein gave us a nice energy equivalence thing. So E equals mc squared, and then that tells us that m equals E over c squared, right? And then we can go ahead and replace E with hf, right? Oh, I'm sorry, I put h here. That should have been a delta h, because that's not the same as this other h. Remember, this h here is Planck's constant. This is delta h. Maybe I should have used delta y, but too late now. But delta h, this is the height. This is Planck's constant. The height, Planck's constant. So here, Planck's constant, E equals hf over c squared. Okay. Come back down here, and we've got hf up high, plus, now replacing m, hf over c squared, right, times g delta h equals hf. And now here we can get rid of some of this confusion, because now there's Planck's constant in every term, and we can get rid of them. And then this is then if we start solving for this, we've got g delta h. Oh, and I'm sorry, this is f high. Sorry, that's its energy up high, the frequency of it while it's up high. My mistake. Forgot to put that on there. So g delta h over c squared equals, now this will be FL minus FU, so FL minus FU over F high. So now we just have all the frequencies on this side, and this works pretty well. This kind of just becomes final minus initial. So this is then just delta F over F up high, and the way this is given to you is actually this form here. I know it's a little different than what I wrote it, but the form you're going to get is delta F over F equals G delta Y. Sorry, I should have made these all delta Y's, but it's just the height over C squared. And this is the version you're going to have to be used to using. And where, of course, delta F is the change in frequency. Delta F is change in frequency. That's always what delta is. And this F is going to be the whichever, either high or low. This will actually work. You can do a similar kind of derivation for sending the photon up. So you take away this just being the up one, and it becomes the measured F. So if you're saying, if I measure it up high and I want to know where it goes down, what it's going to be down low, then this is high. If it's going to be measured low and I want to see what it is when it goes up high, then this becomes F low. So we just, there's no subscript put on that, because just do this same thing but shooting it the other way, and you should get this same result. So this is your nice equation for the red and blue shifting of a photon going into or out of a gravitational well, and into or out of gravity. This is that thing that's believed to be what causes all like the red shifts and stuff. You can look at this as a reason for light being unable to leave a black hole. I'm sure you've heard that before. It's a black hole because light can't escape it. And one of the ways you can think about that is to say, well, here, essentially what happens is this frequency final, like as you shoot something up high, so you'd start with it here, however high of energy of photon, that in order for it to leave, its frequency has to basically go to zero. It has to drop to zero energy, and it can't get out. So at that point, the light shifts. And this will be important too when we go to talk about black holes, of knowing that light blue shifts as it goes into a gravity well, and red shifts as it goes out of gravity. Okay? This is also something you could look at as a way to talk about time dilation. Okay? So we had time dilation before with special relativity, uh, but here's, the special relativity was time dilation based on coordinate system transformations. This one is actual, it seems to be like actual physical changes in this. So you could imagine that if we used the frequency at which a light wave passed us to be a clock. So if I have a certain frequency of light coming at me, every time I see a crest, that's one tick of my clock, right? Well, you could imagine if I sent a light beam up out of a gravity well, right? So sorry, let's go back up here. I send a frequency of light up out of the gravity well. Let me just redraw it, right? So you're on here and you're on some planet, and you send some high energy photon out, right? And every one of these waves that goes by is a tick of your clock. Well, by the time it reaches some guy way out here, right, it's stretched out. And so if he's looking at you doing stuff, like say, every time you have like a little electron here, and every time the electron vibrates back and forth, it creates a new wave, right, a new photon. Well, what's he seeing out here is he sees this stretched out, and so there's a greater period of time between these crests, right? That's not a very good one, so let me redraw that. Let's say it's the same one, but, let me just do it a little, like, better than I had originally drawn it. So here you have this little gap, and here you have a bigger gap, and the speed of light, remember, is invariant. It doesn't change. So if this guy's out here looking at you, and he's counting off ticks of your clock, he's going to see your clock moving slower than you are, while you're down here in this gravity well, and he is not. Okay? And vice versa. If he sends a beam down to you, right, if he sends you some beam like this, by the time it reaches you, it's going to be a lot higher frequency than it was. It's going to blue shift. And so you're going to see his clock moving faster than he does. Okay, so he thinks your clock's moving slower, you think his clock's moving faster, and this is a gravitational shift in time. So, so this frequency can actually explain time dilation, right? So this is gravitational time dilation. Okay, and then we have to be able to calculate that. So it turns out if you go through and calculate this, you can do this from that wonderful Einstein's equation I gave before. You can go through and use what is called the I think this specific derivation comes from something called the Schwarzschild metric, not something called. It's a Schwarzschild metric. Remember I talked about the metric, the little g that was in there. So it's basically from that. I guess I could write this again. R mu nu minus 1/2 r g mu nu. And this was the metric tensor. Well, there is a guy, Schwarzschild, who came up with a metric for a non-rotating, non-charged black hole, like the most ideal situation you could, and it was a solution to this, and using that as the basic idea behind a black hole, we can do this. And what was there? There's some constant here, 8 pi g over c to the fourth, I think, c to the fourth. And then, of course, the stress energy or the momentum energy tensor. But he was able to come up with a metric that I'll talk about more in the next video, but that's where what I'm about to talk about comes from. And if you go through and use that metric and calculate it out, proper time versus dilated time, you actually end up getting near a black hole, so near a Schwarzschild black hole, so near a black hole, specifically a Schwarzschild black hole, near a black hole, okay, so not non-rotating, not charged one, you get that delta t is equal to delta t naught over 1 minus rs over r. And this is square rooted. Okay? And so this is what you get. Delta t is the time, the elapsed time It's basically t far from the black hole, and delta t naught is time near to the black hole. And so let me draw you a picture of how this would really work. You would have to have someone way out here. So over here we have our black hole, right? And RS. RS is called the Schwarzschild radius, and it's basically the radius of the event horizon. So radius of event horizon. And remember, this event horizon, I don't know if you remember because I may not have mentioned it, but you may have heard it before. This is the boundary of a black hole where once you're inside it, nothing can escape, not even light. Outside that, light still has a chance to escape, but inside it, light cannot escape. So this would be RS, right? And then this is going to come all the way out here. This will be, so this is delta t. This is the far guy, and then closer to the black hole, delta t naught. Okay, so it'd be this kind of situation. This is the amount of time that elapses for someone near the black hole, and this is the amount of time for far away. And again, this is the event horizon, which is the point where you get so close that nothing can escape, not even light. Okay, it's that event horizon. So it's often considered the radius of the black hole, the boundary of the black hole, because once you're inside there, it's unavoidable. You can't escape. Okay, I think that's all for now. Make a quick little correction, try and add this on to the back of the other video instead of making two different videos. But I realized I forgot to tell you what this little r is, and it's this little r is just its distance from the center of the black hole, so it's distance to delta t naught location. So it's basically this distance right there from the center of the black hole, this little distance right here. Right, make that darker. That is little r. Okay, that was all.